Welcome everyone. I will be talking to you about my very GenAI generated context is king talk. The subtitle is your RAG pipeline is probably overkill for what you're doing. So let's go into it. The problem that started it all was, for me last year, we were doing a project at one of the banks I was working at earlier, and we wanted to extract ESG information from these documents. But we ran into some problems. So traditional RAG kept failing here, and it was missing critical cross-reference information due to the chunking. There wasn't a standard ESG jargon around within the documents because there was no standardization in what needed to be reported yet. And on top of that, it was very hard to create a ground truth data set due to the complexity and the jargon. So it wasn't just AI that was having a hard time with this, it was also the people themselves. So the question was, with these long context models getting more popular, more diverse, do we even need RAG anymore? So why does this matter to you? Well, RAG is quite expensive. It's not a free solution. You need infrastructure, embedding models, vector databases, and on top of that, it requires a lot of specialized knowledge, whereas a long context window is very easy. You dump it in, it works. And context windows are growing, obviously. In the last 2 years, they've gone from 4,000 tokens to over 1 million. So we don't know where they will be in another 2 years, but chances are they will be higher than what they are today. And the issue is that the performance trade-offs are not clear. So we have models that go to 1 million. What does that mean? Because everyone that has worked with long context models for more than 2 seconds knows that they don't really work that well if they are used for longer. So where's that threshold where we see we start to see them fail? So who am I? I'm Bauke. I'm a research engineer at org. I have a CS degree, computer science. For the last 6 years, I've been working at the banks, at ABN AMRO and ING. And then about a month ago, I went to org, which is a small startup, so quite a big change. This research direction was more of a personal interest sparked by one of these projects, isn't tied to any of these. And last one, I'm also organizer of the MLOps community here in Amsterdam. I've been told that you guys already heard my name earlier today when Demetrius was speaking, so he's my one of the bosses of me that's speaking here as well. And then the second one is Florence, who's also here. And he was my manager at ING, so yeah, shout out to both of them. All right, moving on. So the questions that we will answer today are the following. And these are essentially the research questions I came up with because I was like, I want to understand how this works. So how fast are LLMs? And this is relevant because where RAG scales pretty well, an LLM may not, because we've all heard of this quadratic scaling issue with the attention. So if we put in 1 million, does it take 1 second or 5 seconds or 20 seconds or a minute? And that makes quite a big difference. When do we skip RAG entirely? Where is the performance cliff? And this is the assumption, or based on the assumption that even with 1 million tokens, it likely won't work as well on the whole thing. So where does it stop performing well? The fourth question was, is re-ranking dead? Because if these models are as powerful as they currently are, re-ranking was historically a measure to fix the issue of getting lost in the middle, and that issue seemed to be largely solved. But I haven't seen a lot of people advocating for the complete omission of re-ranking as a consequence of that. And the last one is long context then worth it? Or rather, when do we use it and when do we not use it? So going back to the problem, we were working on RAG optimization for over 6 months. And it started with some 60% accuracy for the project we were working on. We added query rewriting, which gave us to put us to 65. We added re-ranking, a little bit higher again, hybrid search, 70%. Some steady increases, but then we tried to put it into the context window, and we went up to 85. So we were like, okay, what does this tell us about the approach of the project and what needs to change here? Because RAG is a complex method. Like basic RAG is as the name states, pretty basic. But if you want to have a RAG system that actually works well, performs well, finds the things that you have, often you need to add a ton of complexer components in there. So every improvement adds complexity. More components means more failure points. And the chunking does have an effect on these cross-references within the information where you often miss data using RAG. So we come to the context window promise. Will it solve our problems? No chunking means no lost cross-references. No retrieval means no missing information, and no embedding means we get the full text representation, the rich representation of the information. Yeah, it's heavier, but if it works better. In the last year, I guess, many model providers have been scaling up to 1 million. Google was already there for a bit, and now we have Claude, we have Meta, we have Qwen even going there as well. And GPT also went there for a little bit. So that's good. But I didn't really have a feeling for how many 1 million tokens is, right? Is that a book? Is it 10 books? So for nerds like me, it is about 1.3 full Lord of the Rings trilogies. Oh, those are thick books, so that's a lot of data. And for the people working in finance, it is also about 2 annual reports of ABN AMRO, which I found very surprising amount of data in there. So I don't know, there's maybe AI both on the writing side and then on the analysis side of that. But yeah, okay, point is, we can fit a lot of data into these models. So I do want to go on a quick tangent about Claude Code, which is one of the more major applications of context window operations. It uses agentic operations essentially for everything. There's no RAG, there's no indexing or anything. And I was preparing for this talk by writing, the whole plan. I had everything set up in a document, the questions, the hypotheses, the experiments I wanted to run. And I was like, okay, we've come so far with AI. Claude Code works quite well for many things, so how about I just let it rip in this case? So AI goes brr. It did go brr, but not in a good way. So the chaos that followed had an endless list of issues, but among others, I had a checkpoint system that would start over after it had finished, so I have done every experiment about 10 times before I realized that this was happening. It ignored updated features, so it would update a function, and then I would ask it to change something again, and then it would redo the whole thing, ignoring the previous updates. It would create an endless list of files, so I think everyone is familiar with this. We get readmes that are not necessary, we get example scripts that are not necessary, I get 1,000 different classes that are not necessary. And the last one is results and log files for everything. So apart from the functional files, I also have 1 billion files with data that I will never be able to analyze. It breaks in the middle somewhere, those logs are stored forever in the repository. So yeah, a lot of chaos. This is the chart of my Claude Code usage the week before I went on holiday and kind of thought about my life for a little bit. But every dollar equates to about 1 million tokens. So on these days, I was spending 50 to 70 million tokens a day, which is a lot. It really is a lot. And I was going a little bit crazy. This is the class diagram, UML diagram for those that are familiar, of all the classes that Claude had generated. And I mean, there were some interesting research questions, but it's not 60 classes complexity. So I was feeling a lot like this after that week. I went on holiday and kind of thought about my life. But the takeaway from this, and I think also a good takeaway for you, is that you still need to spoon feed a lot when the context is complex. So to specify some issues that I ran into is incomplete searches was a very big one, where using the agentic search, it finds like 5 files that are relevant, sure, but it also misses 5 other files that are also relevant. Memory is very sporadic and incomplete. I have both Claude MD and Mem0 integrated, which both are never used. Or Claude MD is used at least as input, but it never writes to it. So I don't know, yeah, the added value seems very limited. Larger repos are inherently a little bit more tricky with agentic search, so that's fair. And that's where solutions like Cursor's one, where it does index everything, works better. But that's no excuse, right? I'm paying a lot of money for this product. The fourth one is it can make huge changes based on partial information. So when you lose attention for just 1 second and you don't find the error in the plan that it was making, suddenly you have 10 additional files, 5 extra classes, and 5 new CLI tools that you didn't know you needed for this, and you probably don't. So last point, yeah, it's not going at knowing when it doesn't know enough. So asking clarifying questions, it happens sometimes in deep research, but the models are not tuned to do that structurally, which is, I think, the base, the root cause of many of these problems. And on top of that, size isn't just increasing. So many models are increasing their sizes, and in a trend, or like over the whole thing, in general they are, but Gemini went from 2 million to 1 million tokens for their largest model. Llama 4 Scout, which is a 10 million model, only is available from in 1 million, and only from third parties. So Meta's own version is only doing 128K. And lastly, Claude Sonnet 4, 1 million, which was a huge thing, and suddenly we have long context from Claude. It isn't in general availability anywhere, it's in beta. So I wasn't even able to test it for this talk as well, and I was kind of looking forward to doing that because it is an interesting model. So back to the problem. So we had this ESG project, we had the issues that we were facing, no ground truth data sets, no standardized jargon, and traditional RAG kept missing important details. And RAG has the additional issue that there's an endless list of improvements that you can do to the system, and none of these is wrong or correct, so you kind of have to try them all. And without a good data set, it's very hard to evaluate them then. So yeah, it really boils down to this question: when do you use RAG and when do you use the context window? So outline we'll do, apart from the 15 minutes of our talks that we've already had, we'll do 3 sections, one about speed, second about quality, and the third one goes a bit deeper into RAG. So how does latency change with the context window? And this is important if you are doing thousands or millions of calls, because the difference between 1 second and 10 seconds and a minute is obviously huge. And we've heard this term quadratic scaling for LLMs, right? So if the input increases by 10x, then the latency or the processing power required is going up 100x. So the question is, they likely have some engineering tricks to make this better than quadratic scaling. How well did they do? Luckily, it is much better. So the dotted line here is the actual quadratic scaling, which is horrible. And they are doing much better. So you're seeing on the left side is a log-log scale, because it's going in increments of 10. So the 2 logs make sense, but it's a bit hard to interpret. But the good thing is you see an almost straight line up until about 10,000 tokens, up to, between 10,000 and 100,000 tokens, you see an increase. And then when we start to move to 1 million, the increase becomes worse. And so the question is, when we do this 10x in tokens, what is going to be the x in latency? And we see, I think, I have a slide here. So going from 100K to 1 million, the multiplier is between 4 and 10. But that's the highest that it will get before this, and each other increment has a lower multiplier. So that's really good. We see here that Google is generally the fastest, and also the only one that goes to 1 million. And Claude is just structurally the slowest. But it doesn't matter if you like the quality, but it is the slowest provider that we have. I think that's all I needed to say here. One other thing that is interesting, and it ties into the processing duration, but is the amount of tokens that are being processed, which is just amount of input tokens divided by duration. But you see that it starts to flatten out with the Google model. And assuming that it does really flatten out, obviously that means that if after that point you start to increase, we get a linear increase. So if the context window starts to 10x at that point, then suddenly the delay also 10x's. I wasn't able to go further than this, but that's kind of the assumption or the conclusion that I pull from this. If we look at this relationship and we try to eyeball it, it looks good, but I did try to make it a bit more scientific and plot a second order polynomial to this to see if there was actually no exponential relationship. And so an exponential relationship in log-log charts is just a quadratic, exponential relationship, quadratic relationship is just a curve. We get pretty good curves here with an R squared of 0.7 to 0.75, which is good if you don't know what that number means. And the coefficient here is very low, right? But the point is there is a coefficient that is non-zero, meaning that if we do extend beyond 1 million, that coefficient will start to play a big role in pushing up that number. So I think this, for me, kind of tells the story why many model providers are kind of putting the boundary on 1 million until we have some great engineering breakthroughs that push that coefficient even lower. Let's take a look at model speeds, because I think it is interesting. So for Google, it's very beautiful. I think they have a very clear three-tiered system where lighter models are also faster. To me, that makes sense. Does not to OpenAI. But so the point, they reliably scale to 1 million, that's good, and they're faster. For GPT and Claude, that doesn't really hold, so they're more kind of bunched together. We see, I have a pointer here, we do see here a little bit, the green one is GPT-5, so GPT-5 is surprisingly the fastest for most of the context windows. With Claude, there's not really any structure to be found. And altogether, we see the top blue line is Gemini Flash Lite, so the cheapest model of Google. And then here, the turquoise one is Gemini Flash. So you can see that anywhere above 10K, the two Google models are actually the fastest. And the rest is kind of in the middle. GPT-5 does well up to 1K, which, that's not that much. Maybe they just have good servers and higher bandwidth. I don't know. So takeaways from this: scaling beyond 100,000 tokens is quite costly in time. Gemini is often fastest, and while slower, scaling does much better than quadratic, which is very good. So moving on to the second one, which is context windows. How well do they work? And so for this, we need to understand what needle is in a haystack is, which is a benchmark where we try to find some answer to a question that we have put in that context, and we can kind of vary the length of that context, but generally it's a very long text, and we put the answer somewhere in the middle. And then the LLM has to find that answer. So an example can be, what color was the duck I had as a child? Then a needle would be, the duck I had as a child when I was 10 was orange. And then we would put this in a book, The Lord of the Rings, for example. And this matters because this is kind of the benchmark that every model provider shows on screen about how well their model is performing for long context. This is for Llama 4, the release, and we see Maverick, Scout, and another Scout. The middle one goes up to 10 million tokens, and well, these two, they are flawed, but this one doesn't have any flaws. If you've ever been a data scientist, you know that anything that scores 100% on accuracy or whatever is very suspicious, and this is also very suspicious, because if it is 100%, you know it isn't 100% if you've worked with these models. So where does the truth lie? So the question becomes, how do they work for non-trivial tasks? And for this, I need to introduce my shadow co-author, because Chroma Research published on basically exactly this topic while I was preparing for this talk. I didn't have any results yet, so I'm just going to walk you shortly to what they found, because I think for any AI engineer, this is extremely relevant to be aware of. So shout out to Kelly Hong, who's the lead researcher on this, this work, and check it out if you have time. It's called Context Rot. It's a really nice read. So experiment 1 is the effect of similarity between needle and haystack, meaning if you have a question and an answer, how different are they in their semantic similarity? So in these benchmarks, they are often, they have quite high similarity. Also lexical, like the words can be the same. But many real-world situations do not have this, right? So your question and the answer will be very different. So they created 2 groups of needles, for this case, split on cosine similarity. One is very similar, and then the other one is not so similar. And these were their results. So the chart shows on the left side models that are have a context window less than 500K and are high performing. So they split up all the models in high, medium, and low. I'm just showing you high because this is already not great and the rest is just worse. And this one is the models that go above 500K, which is just the Google models in this report. What you can see here, the blue line is the similar group, and then the red line is the dissimilar group, which you can see drop down in both of the graphs. So here it starts about 10,000 to 100,000. It's still okay, right? 80 is not terrible, but if you look here, going to 1 million, yeah, 40 is nothing. We cannot work with 40. So the takeaway here is dissimilar question answer pairs are very challenging, especially after 100,000, and smaller models perform worse much faster. So I didn't have time to show all the charts here, but it was quite bad. The second experiment is the impact of distractors, because often there won't just be one piece of text that is related to the answer. It might be 5 or 10 different things that have very similar information, but doesn't quite answer the question. So they added incrementally a number of distractors, which are pieces of text that are very similar to the answer. And yeah, well, this is kind of how it looks like in a diagram. So distractors in the case that we had earlier with the duck could be my brother's duck was blue, the duck I had as an adult was purple, and my childhood pig was pink. So all kind of in the same realm, but doesn't answer the question that we had initially asked. So in context of a coding agent, I think this happens a lot, right? You update some function, that function stays in context window, you say, oh no, add this thing or do this little bit different. It just adds a different version of that same function into the context window. So in terms of distractors, everything except the last version is essentially a distractor. And while we do have the option of doing smarter things with context windows, at this moment we are not doing that, and we are not removing these old versions. So this happens a lot. So how did they do? Yeah, not that great. So one distractor is still somewhat okay. Oh, that's not the right button. One distractor is still somewhat okay, which is the yellow one. But the red is the 4 distractors. It's just going really bad. So for both context sizes, we can see they end up here at 60% and here at 35%. And that's just 4 distractors. So that's, it's bad, but it's not terrible. They also dug into the error analysis to see if models fail differently. And one notable result that they found was that this is the result for Claude, and Claude in, 74% of cases abstains from answering the question. So it's not answering incorrectly, it's just saying, I'm not able to answer this given the context, or at least it's refusing to answer. The other models are quite different, so GPT is over here. It just goes full hallucination, just whatever, some of the answers are in there. And the rest of the models are a little bit in between. So they have Gemini here, and then they also tested Qwen on this, performing quite similar. So takeaways, distractors are detrimental for, all models. Smaller models absolutely crumble with this test, so I think they went down to like 5%, and more distractors generally worsen the effect. Experiment 3. This one is about long conversation QA. I think this is a very interesting experiment. The question here was how much worse do they answer with a lot of context? So they looked up the segments of the text that were relevant to answering the question, and in this case it wasn't just simple single-hop questions. They had complex, multi-hop or temporal questions for which you needed quite detailed information. So they extracted the relevant parts, gave that to the LLM, and then the alternative was we give the whole text to the LLM, both with the same questions. On average, 113,000 tokens. So that's a lot of text. I don't know how many Lord of the Rings that is, but it's a significant chunk out of there. This is the result for Claude, and we already talked about this abstaining from answering thing that Claude does, and that's something that happens here as well. So you can see here in the red is the focused context answer, so just the relevant part, and then in blue is the answer it gave for the full context. So we see Opus Thinking here is having the highest score. It's getting pretty okay, 72 with the full context, but only 38 if it's non-thinking. So we see an almost 2x increase just by enabling thinking. I think that's a pretty stark difference. Same goes for Sonnet in this case, and then the rest is just not that good. But what is notable here is that Sonnet 3.7 and 3.5, they answer better as a non-thinking model than the non-thinking versions of Sonnet 4 and Opus 4. For Gemini performs really well here, both in thinking mode and non-thinking mode. And so they don't have this anti-hallucination training, and Gemini is just, I'll just answer, but it does also answer it correctly. So the threshold between not answering lies somewhere, and I don't know really how to think about, is this a good thing or a bad thing? It depends probably on the situation. To note here, 2.5 flash thinking also gets an 85. So this is the mid-tier Google model outperforming even the most expensive Claude models that were present. I don't have GPT here because it's just kind of in the middle. It's not really remarkable. Takeaways: long context Q&A is very much unsolved, very much unsolved. Reasoning helps a lot, especially for these models that have the urge to be sure before they answer, but hallucination prevention can also backfire, as you saw. So keep in mind that this was only with 113,000 tokens, which again, it's a big chunk of text, but it's also just over 10% of what these 1 million context token size models can do. And this is the last section. So this is again something that I looked at, which is the impact of re-ranking, and does re-ranking still make sense with long context models? So the experiment setup was as follows. I created 2 RAG types. So one was basic RAG, it's just an embedding, search, retrieval, let's go. And then also an enhanced RAG, which does query rewriting and was it called HIDE, hypothetical document embedding. Just searches with that, and then retrieves based on that. Re-ranking, yes or no, is of course important, and then as baseline, the full context. This was applied to a Wikipedia data set, so there were questions about the Wikipedia article, and it would look within the Wikipedia article. The context window usage of this is not as big as previous experiments, so you can see the purple line is the full context version, which is on average about, was it 28K tokens, so it's also not small. And 50 chunks, which was, we'll see, 50 chunks is about 20. I went a bit further and also tried to do, okay, what if I just do 100 or 200, or we'll see later how that works. But this is about 40 to 50 pages to 28K, so it's a reasonable size of data. I want to talk about hit rate quickly, because with RAG you always have this balance between do I look at retrieval metrics and which retrieval metrics should they be versus is my question actually answered correctly, and there's this this split in metrics that you need to look at. So the hit rate is kind of a weird version of recall, but it means was the ground truth chunk, was it in the context? So you can see that steadily rise, and it kind of flattens about 50, which I thought was pretty late, because the number of chunks that are in these documents, I think, is on average about 200. So it's almost a quarter. Yeah, and we see here more chunks means a higher chance of the right chunk. And every line, sorry I didn't explain, but every line is one of these experiment configurations where we have rag plus and minus re-ranking, and then advanced rag plus and minus re-ranking. So we don't see a big difference there. This is the correct answer percentage for each number of chunks for each configuration. Not the ground truth, but the full context ones, it's at about 92%, and we see that the RAG versions kind of converge to that point as well. We see some distress here in the middle, but overall they kind of increment side by side. So what is the effect of re-ranking? So on information retrieval metrics, it's quite a lot. This is the percentage improvement that re-ranking gave for these metrics at different values of k. So k is the number of retrieved documents. So MRR, you don't have to know what it is. That increased. The other one, I see I labeled it incorrectly, but that's a recall at 10. It also increased significantly. So that's good. The issue is that for the actual answering of the question, it didn't really matter. So we do see a spike at 10 chunks, which I was a bit surprised about. But then when we pull out the experiment to more and more chunks, that advantage started to vanish. So I'm inclined to consider this more of an outlier than a structural indicator. And we do also see it negatively impacts in some of the cases. I don't think this is a structural thing, but I do think it doesn't really add that much. So this is kind of the same data, but in a heat map, so you can see all the details. So 50 chunks saturates this is correct metric, so answering the question correctly. That is a very use case dependent parameter, right? If you have more data or you have a different type of data, that number could shift, but try to find this number for your use case, because that will tell you, do you have the right value of k? And yeah, in my case, it was 27% of the average document length, which I was really surprised about. So you might get better mileage from your thing, but I'm not sure what to take from this. If you have 100 million chunks within your RAG database, yeah, you're not going to ingest a quarter of that. So yeah, you have to look for yourself. Yeah, I think that's kind of the takeaway from this. A good extra thing is to look at the speed that we have here. So at the bottom is the base RAG. And then at the top we have the enhanced RAG with and without re-ranking, and then the red line is the full context version. And you see that the enhanced RAG and the full context version are pretty similar. So in terms of execution in a production setting, yeah, it doesn't matter that much. Some limitations. The query complexity here was kept intentionally limited because I didn't want to fall into the trap that my questions were too complex and it wasn't performing as a consequence of that. So the questions were kept fairly simple. I didn't apply re-ranking for filtering, which is not so much a limitation, but rather a different direction of research that I think is interesting. But for example, that could mean we don't just retrieve 20 chunks and then re-rank those, but we actually retrieve 500 chunks and then we re-rank and then we take the top 100 out of that. I do think that could be a valuable avenue of research. The max number of chunks I had was 339, so that's not that much. There's a lot more, so I would say experiment a little bit. Limited set of models, and I only used one embedding. I don't think there will be structural improvements or changes with different embedding models, but obviously some of these numbers will change. Takeaways, you need a much higher K than you might think, and result re-ranking didn't really have an effect, at least in these tests. So key conclusions, how fast are LLMs? Well, scaling beyond 100K gets quite expensive. It's about 5 seconds at 100K. It's about 20 seconds at 1 million. You can use these as kind of guidelines for your use cases. We saw a 4x to 10x increase from 100K to 1 million, which likely is higher beyond that. Gemini offers the best speed at scale, and it's better than quadratic, but there can still be significant costs when we start to scale these models. When to skip RAG entirely, it's a little bit the same answer. So if your domain fits in 100K, you should skip it. It doesn't make sense. Performance does degrade sharply after 100,000 tokens, and distractors become increasingly problematic. So the speed between RAG and long context is comparable at this scale of data, but obviously if you do ingest more data in long context, it will take longer than a RAG pipeline might. A RAG system is in general, I would say, more scalable than long context. So where's the performance cliff? We keep coming back to the 100K. Long context Q&A is still very much an unsolved problem. Distractors are very problematic for every model intelligence level and every model provider, and even at 113,000 tokens, performance varies dramatically between them. Number 4, is re-ranking dead? Yeah, I think for modern LLMs, it is in most cases dead. Retrieval metrics do improve with re-ranking, but the actual answer quality does not. So yeah, the modern LLMs, they handle noisy context way better than previous models. They don't have this gap in the middle where somehow attention doesn't work anymore. So it just doesn't make sense to add it. Especially if you have latency from re-ranking models, you have maybe inference costs from re-ranking models, you have complexity from there as well. So yeah, is long context worth it? I think in general, yes, but there is a balance. So most systems won't be able to rely just on long context and will need to use a RAG system on the side. So for the LLM that you are using, find a point up to where the LLM is working very well, right? So that could be the 100K win threshold, or it could be slightly before or after that. And then just retrieve as many chunks as fit within that size. That would be my main recommendation. So for me, that was about 50 chunks here, not that fit in the window. You could put in the whole document, but that was at least a point where you have this saturation. Higher retrieval numbers compensate for embedding limitations, because that's, I think, a way to think about why, for these more complex questions, it fails to retrieve the right thing. And so the limitations of the embedding search, or whatever search you are using, can be compensated a little bit by just retrieving a lot more. And obviously, answer correctness in the end matters a lot more than these retrieval metrics. While they are important, they are not the end goal. So your new RAG decision framework, when to skip RAG if it is less than 100,000, or when you have a complex domain, I would advise you try to look elsewhere first. When to use it, if it's more than 100,000, for sure try it. Yeah, use up to the 5K or 50. Use up to 50K context chunks. Yeah, that was kind of where I found to be that balance point. And especially if you have simple queries, it should be okay. So what you should do on Monday, audit your RAG pipeline. Is your domain less than 100,000? Try the context only for small domains that you might find coming in. Experiment with a larger number of chunks. It could be 20 to 100. Make it 500. Tailor it to your use case. And question your re-ranking steps, because they might not help, and yeah, might be adding a lot that isn't helpful. So let me summarize it, because VO came out, so I have to do a VO.
Might be overkill. Is your domain under 100K tokens? Try context only for small domains first. Skip the complexity day. Context is king. Questions about your specific use case? Find me after the talk. Let's solve your context versus RAG challenge together. Context is king, but implementation is everything.
Thank you. Two quick acknowledgements. So Sarp and Tony, the co-founders of Org, for giving me the LLM access, because I burned a lot of tokens for this. And Kelly Hong for Chroma. Check out our article. It's really nice. So if you want to connect, scan this or come to talk to me after. Thank you. Yeah.
Thank you, Bauke, for the great presentation with some practical insights as well. We have a couple minutes for Q&A now, and there's a mic that's going to go around the room. So if you have a question, please raise your hand. There's a gentleman there.
Which one?
Mic is coming your way. It's a big room.
Yeah.
Hi, thanks for the talk. Very interesting. I was wondering, you were saying about the re-ranking, it doesn't really add much, but let's say that you have more than your retrieval system gets more than 50 chunks, but then you want to decide which 50 of the 100 you want to put into your LLM. So isn't that where the retrieval helps?
So it depends on how your pipeline is structured. At least from my experience, typically it was you have the retrieval that kind of will determine what goes into the LLM, and then the re-ranking helps in pushing the relevant chunks to the top where the LLM works better, quote unquote. If you do use it, like you're saying, like as an extra filtering step, I do think that is valuable, and that's not what I'm advocating against. What I'm saying is, yeah, rearranging the order of the chunks within the context window doesn't really help.
Okay, thanks.
Any other questions? On the front, I see some hands.
First of all, thanks for the nice presentation. It was great insight from your experiments. So my question is regarding the security concern of the context window. So like there will be a opening up more securities if you have a context window which is long enough. So how you handle that? The surface area of the context is increasing, and then there is a data leakage and etc. could happen also. Also, the model could lost in the middles before answering. So, how do you handle that in the use case where it is less than 100K tokens?
I'm not sure I understand what you mean with there's data leakage with a larger context window.
Meaning that when you're using the large context window, meaning that you're using more data, meaning you're opening up more surface area.
You're giving more data to the providers.
Yeah.
Yeah, that's if there was the option that there could be private data in there already, your use case should already be built around that, right? So strip out PII or have some agreement with the model provider. I don't think that increasing the context window should play a factor here. You should have it already in place, or if not, you should do it. But yeah, increasing the window size shouldn't matter for that.
Yeah, because the RAG is actually embedded in the hash methodology and etc. And also filter out those. So do you have any technology in this flow you have described, context route?
I don't think so, but maybe we can talk after and discuss this further.
There are two gentlemen in the back there. They're avidly raising their hands.
Thank you, Bauke. I think it was a great presentation and really relevant. I have two things. One is a comment about the models you use for the experiment. I think it will work to also not only separate by LLM provider, but also by the type of model. Because I saw that there was a mix between reasoning models and conversational models. For instance, using GPT-5 versus using other kind of models from other providers. And it will be more relevant if you can also do that per type of model. For instance, all conversationals versus conversationals, and the other way around with reasoning models. That could improve a lot and well, bring more really information. And I have a question about how you evaluated the accuracy and correctness of the different answers you get. Could you explain a little bit more on how that was done?
Yeah. Yeah, accuracy here was done with LLM as a judge, which just compared is the answer the same as the ground truth. So there may be some errors in there, but in general, because of the questions aren't that complex, that it should work pretty well. And we do have like coded metrics for the retrieval, so we do know that the answer, or whether the answer is in the context window or not. But for the reasoning, yeah, good point. That would be an interesting direction to look at.
I'll have a final question here at over two. We can do two more.
Thanks for the talk. One question. I think we've seen in your data that, or in your experiments, that distractors is really one of the main issues explaining why some models answer badly. It seems like thinking models are actually a good way to mitigate that. I do believe it's because they might reorganize the context so that maybe the relevant data is better located or just more prominently present inside the context. RAG could also be a way to solve that by just retrieving only what's correct, but your experiment's shown the opposite. Where would you say is the best leap forward we could make there? Maybe is there other approaches that I'm missing that you can see as a good way to improve accuracy and performance of such applications?
I don't think the RAG or not using RAG or not using RAG won't influence the distractors in that sense, depending. So if the context size is the same, they might have a similar amount of distraction also, because if you do use RAG and you look for similar chunks, then inherently you will get text that is very similar. So maybe that increases the problem rather than diminish it. In terms of, yeah, that problem, I don't really have a concrete takeaway for it. I don't have a mitigation for it. I just think in terms of the general approach here is a balance between the two systems is likely the best direction that you could take, where you have some retrieval step, because typically the data will be too large, and then you enhance, filter that to go into the LLM that eventually answers the question. Hope that helps a bit. Yeah.
Okay. Final question.
Thank you very much. Yeah, so I was kind of wondering, you've shown a lot with benchmarks for needle in the haystack, looking for an answer in a large context. But I'm also curious, especially because you said like Claude often refuses to answer if it's not sure, if there's kind of an opposite benchmark where you go look for an answer in a large context, but the answer is not there. How many models actually correctly answer that they cannot find it?
Yeah, I think in that benchmark, Claude would do very well. I don't think, it was not in my experiments, and also in the article there was, it wasn't researched specifically, but I think the kind of the intuition or the nudging in that is that most of the models would either find an answer that's related or just hallucinate, and then Claude is pretty well at not doing that.
And do you know if there's any specific benchmarks that already exist for this task?
Not that I don't know them, at least.
Okay.
Yeah.
Thank you.
Yeah. It would be very interesting to see. Maybe next year.
Okay, and that concludes this talk. And then I would like to ask for a final round of applause for our presenter, Bauke. Woo!